Hello, everyone. I am Afid Bandimarad, and today I'm going to talk about the generation of highly ion conductive polymers for application in lithium batteries. A lithium battery consists of an anode, a cathode, and an electrolyte. The lithium ions traverse the separator through this electrolyte. And current technologies use liquid electrolytes, but these are flammable and they can explode and they can leak. So to overcome these limitations, we propose to use solid polymer electrolytes to replace the liquid electrolytes. But to achieve this, we need to have highly conductive polymers. So the list of polymers is very big, but not all of them are conductive. So we have found a list of 229 unique conductive polymers, and we propose to use machine learning to expand this list. So we use a variational autoencoder. We start by representing the polymers using this mass representation. In this representation, each character represents either an atom or a bond or a chemical structure, like a ring. And then we use this one-hot encoding to translate this Mars representation into a matrix of numerical values. Then we feed the matrix to the encoder, and the encoder tries to learn the mean and the standard deviation of the input. And then we use the learned distribution to sample a latent vector that we feed to the decoder, and then we get an output that is a matrix that we decode again to get this mass representation. And during learning, we try to reconstruct the input. And then after we finish learning, we can just use this distribution and sample new conductive polymers. And here we have the results of our work. So this figure shows the loss versus the epoch. So the blue line represents the reconstruction loss, and the orange line represents the KL divergence. And the KL divergence represents how far we are from the normal distribution. And our goal is to minimize both losses, the reconstruction loss and the KL divergence. And here we have some examples of the output. And as we see here, not all the output is valid. For example, the first and the third one are not valid, while the second one is valid. And this polymer is represented here in 3D and here in 2D. So the main limitation of this variational autoencoder is that it produces some valid and some non-valid polymers. And to overcome this limitation, authors in the literature have used grammar. For example, Guo et al. In 2022 used a graph grammar. So they start by representing the molecule using a graph grammar, where the atoms are represented by the nodes and the bonds are represented by the hyperedges of this hypergraph. And then they learn a grammar from the database. So for example, here, the algorithm learns these 4 grammar rules. And then when we start with this initial node and we apply these different rules to the node, we obtain the final configuration of the molecule. And then we compared this algorithm with ours, and we obtained these results. So we compare the 2 algorithms using 3 metrics: the validity, the uniqueness, and the diversity. And so the validity and uniqueness are defined by the percentage of chemically valid or unique molecules, and the diversity is defined by the distance between 2 molecules as defined in this paper. And as we can see in this table, for the 3 metrics, the polymer grammars outperform the SMARS VAE. And this is the main result of this poster. Thank you so much.